2025 A-Level Combined Mathematics Paper 1 Part A question number 6. The question says, let k be greater than 0. And then it says, the region enclosed by the curves y equals e to the kx minus e to the minus kx whole thing squared times the square root of e to the kx plus e to the minus kx, and y equals 0, x equals negative 1 over k, x equals k is rotated about the x-axis through 2 pi radians, which means we have some curve which looks like this, and this curve has some area that is enclosed by these lines, which are the line x equals negative 1 divided by k, x equals 1 divided by k, this line here which is the x-axis, or y equals 0, and this actual curve. So we have this area here and this area here. So we're saying that this area is rotated about the x-axis through 2 pi radians. So it's rotated like this, a total of 2 pi radians around in circle, to create some sort of three-dimensional shape that looks like this and has some internal volume. So what they're asking is to show that the volume of the solid thus generated is 2 pi divided by 5k times e minus 1 divided by e to the power of 5. So we are expected to show that the volume of this solid here that I've just marked out with scribbles is going to be equal to this equation that they have given here. So what we need to do is to first establish an expression for that volume. So as we know, the volume of such a revolution v is going to be equal to pi times the integral from the starting point to the ending point, which in this case is going to be 1 divided by k, negative 1 divided by k up to 1 divided by k of the function squared. So the function, this being this thing here, which I could represent with y squared, integrated with respect to x. Now if we substitute the actual function into here, the actual function is going to be this function squared, which if you square the first part is going to be e to the kx minus e to the minus kx to the power of 4, since if you square the square it's going to be the power of 4, and then we need to multiply this square root by itself, which when you multiply by itself is going to give us the internal bit, which is e to the kx plus e to the minus kx, and this needs to be integrated with respect to x. So this right here, this entire expression is going to give us the answer we're looking for. Now all you have to do is simplify it. Now, in order to simplify it, you actually need to use a clever trick. You need to see that this thing here and this thing here share an interesting pattern, and that pattern can more easily be seen if you divide this bit by k and put a k on the inside as well. So what we're going to do is exactly that. We're going to divide this part by k, this pi by k, and we're going to multiply the inside by k. Specifically, we're going to put the multiplied k into this term here, and you'll see exactly why this is so useful once you do it. So we're going to do that. We're going to rewrite this as being equal to v equals pi divided by k times the integral from negative 1 divided by k up to 1 divided by k of the same thing, e to the kx minus e to the minus kx to the power of 4 times this bit. And what I'm going to do here is to take this 1 divided by k that I divided and replace it with a k here. So we have k times e to the power of kx plus e to the power of minus kx times k. Now here I'm additionally going to do another step. I'm going to replace this plus sign in the middle with a minus sign. So now we have that, and that's integrated with respect to x. Now observe an interesting property here. If you consider this part here and this part here, we can see if we take the derivative of e to the kx, we're going to get k times e to the kx, which is exactly this part here. If we then take the derivative of e to the minus kx, we're going to get minus k times e to the minus kx, and then this negative here means that we have negative k times e to the minus kx. So we can see from that if you take the derivative of this whole thing on the inside here, this e to the kx minus e to the minus kx, and you take its derivative, what you're going to get is exactly this thing here. So this thing right here is the derivative of this component on the inside. Now, why would this be useful at all? It will be useful by the fact that if you want to do a u substitution where this becomes u, then du will be exactly equal to this part here. Since this part here is du by dx. Since if you take the derivative of this thing with respect to x, you're going to get du by dx. If you then multiply that by dx, you're going to get du, which is all of this stuff here. So therefore, if we want to do a substitution, this thing right here is going to be extremely useful. Now, as you can probably guess, that's exactly what we're going to do. We're going to be performing substitution on this volume here in order to get our final answer. So what I'm going to do here is just make this a little bit smaller. This is how you'd normally write. I just wrote it a little bit bigger so I could explain it better. Now what we're going to do is to do a u substitution, where we substitute this thing on the inside here with u. So we're not going to write it like this informally. We're going to go to the next line and we're going to say properly, let u be equal to this thing on the inside here, which is e to the kx minus e to the minus kx, and then doing that we can see that this is going to mean that du is going to be equal to this thing's derivative, which we already established is equal to k times e to the kx plus k times e to the minus kx dx. So now we can see, if we were to substitute u for this thing here and then get u to the power of 4 for this term here, the rest of it, this whole bit, would turn into simply du. Now, before we can do the substitution, there's one more thing we need to do, and that's to work out the limits. So here we can see the lower limit is negative 1 divided by k and the upper limit is 1 divided by k. So we need to figure out what the values of u are going to be when x is equal to these two values. So in the next line we'll do that, when we'll say when x equals minus 1 over k, u is what? Now if you substitute minus 1 over k for x into this thing here, we can see we get e to the power of k to the power of minus 1 divided by k, which is going to be e to the power of minus 1 or 1 divided by e. And on the other side we have minus e to the minus k times minus 1 divided by k, which is going to cancel out to just 1, since minus k times minus 1 divided by k is going to equal 1. So we have e to the power of 1. So we have 1 divided by e minus e to the power of 1, or just 1 divided by e minus e. So that's going to be lower bound. As for the upper bound, when x is equal to k, which actually I'll write x when x is equal to 1 divided by k, as in the upper limit 1 divided by k, then what we're going to get is that u is equal to, now if you substitute u, x equals 1 divided by k into here, the first term is going to be e to the power of k times 1 divided by k, so e to the power of 1. So just e, and then minus the next bit, which is going to be e to the power of minus k times 1 divided by k, which is going to be e to the power of minus 1 or 1 divided by e. So therefore these are the upper bounds and lower bounds. Now if we substitute these into the original integral, we can see that the integral becomes v equals pi divided by k times the integral starting from the lower bound, which is 1 divided by e minus e, to the upper bound, which is e minus 1 divided by e, of this internal bit here, this bit to the power of 4, which when you substitute is going to be u to the power of 4 times this bit here, which when we substitute, as we found, this whole entire expression is simply du, so we simply replace it with du. And now we can simplify. This part here is going to be pi divided by k, and then we're going to have the definite integral from 1 divided by e minus e to e minus 1 divided by e of u to the power of 4 du, which is going to be u to the power of 5 over 5 integrated from 1 divided by e minus e to e minus 1 divided by e. Now we can see if we substitute these things into here, what we're going to get is pi divided by k multiplied by this bit, which is going to be, if we substitute in the limits, if we substitute u to the power of 5 for this bit here, we're going to get e minus 1 divided by e to the power of 5 divided by 5, and then minus the second limit, which is going to be the lower limit, which is going to be 1 divided by e minus e to the power of 5 divided by 5. Now we can see, since this power is odd, multiplying by negative 1 is going to be the same as just swapping these two around. And when we swap the two around, we can see this is exactly identical to this e minus 1 divided by e to the power of 5 that we have here. So we can see therefore that this is equal to pi divided by k times double this bit, which is e to the power e minus 1 divided by e to the power of 5 divided by 5. And finally, if we structure this to the form that we've given in the answer, we can see the 2 comes to the pi to make the 2 pi, the divide by 5 and the divide by k structure together to become the divide by 5k, and the e minus 1 divided by e to the power of 5 remains as it is. So if we write that down nicely, we can see finally that our answer is 2 pi divided by 5k times e minus 1 divided by e to the power of 5, which is our final answer that we were expecting. So you can see, it is very important that you identify that this little component here is going to enable us to easily do this u substitution, because this component here is the derivative of this part on the inside with respect to x, and therefore if you do a u substitution with this component, this thing is going to easily give you that du is equal to this part dx, which means this whole thing cancels out, giving just du. Now finally, if we discuss the marks given for the original writing of this equation here, where you establish the fact that you know that the volume of revolution is going to be equal to this, it's going to be pi times the integral from the limits of this whole function squared, which is important. You need to identify that this function needs to be squared and then integrated with respect to x, and if you identify that, you get 5 marks here. And then when you identify the u substitution you need to do, for the u substitution you get 5 marks, and for identifying that the du becomes this part, you get another 5 marks. Then once you do the substitution correctly, if you do the substitution and you get to this point, you get another 5 marks, and then if you evaluate the limits correctly, substitute them incorrectly and get the final answer, you're going to get another 5 marks. So therefore, it is important that you first off identify the formula for the volume of revolution, and then identify the components that you're going to have when you have a u substitution, which is going to be the u substitution part and the du substitution part, and then you need to substitute correctly, evaluate the integral correctly, and obtain the final answer, and all of that gets you the total marks that you get. So that's going to be all for this video. I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching, and goodbye.